ECE 312, 332, and 342. And today we're going to talk about our knowledge integration 5, the signal receiving circuit of a radio system. And here we have, in the highlighted region, is the basic circuitry and all the components in order to make the system happen. Alright, so quick overview. We'll start by looking at each component within the system, what it does and how it feeds into the next component. And then we'll look over an analog versus digital signal for potential going through a system like this and how it's processed throughout it. And then we'll look into a more commercial generic example with using a block diagram of the practical components. And then we'll go through the signal flow, how it goes and is edited through the system and comes out the other end as a voice signal from the receiver. And then we'll go into more on filters and then the antenna itself, as it's in a very important piece. So how does each component work? You start off with the antenna, which captures the signal from the RF frequencies, in this case radio frequencies, goes into the diplexer, and this is on or off depending on whether it's transmitting or receiving, and it's all electronic. And then it goes into the bandpass filter, which singles out the signal that we want and gets rid of out of frequency signals. And then it goes into the low noise amplifier after it's demodulated, and this is focusing on amplifying the signal without adding more noise to it, so we can, because it's already got a lot of noise from its input, we don't want to add that to it from an amplifier. And then it goes into the mixer, which takes that carrier signal from a very high frequency in the gigahertz range and converts it to a baseband signal in the 24 kilohertz range, which is audible like the vocal range. And then it goes into the amplifier here in the low pass filter to get it large enough to go into the analog to digital converter to digitize the signal. And here we have an analog AM signal. So here this blue line is the regular voice signal, and this is your carrier signal, and it's operating on a much higher frequency, 1.8 gigahertz in this case. And from this AM signal, it's amplitude modulation, and each, like this bit, will be corrupted by noise here in green, and it's a 16-bit signal. And we don't use these much anymore, but it's a good example. Crossed with digital over here, which has less noise and it's much cleaner, and we can get higher bandwidth out of it, 32 bits worth. In each component here, each little piece is a 1 or a 0 in the signal. Alright, and now we go to the more commercial example. So we have our low noise amplifier again, and here, pardon me, this does the bandpass filter to separate our signal out from everything else, and it amplifies it at the same time. Then it goes into the mixer here, which moves it into a low pass filter for the downward conversion after the multiplication of the signals, which can be seen here by the X. And then it goes into the the low pass filter here, and then the programmable gain amplifier, which takes, like, say, a loud person's voice and lowers its gain so it's not too much to handle, and then a quiet signal so it maintains that gain of whatever we want. And from this, it all has good swing, and it goes into the analog to digital converter to get it into a digital signal, similar to what we saw before. And here we have the more signal side. So this is the signal we want. This is the bandpass filter carries this, gets rid of these out-of-band interferences from the antenna. It's brought in, the bandpass filter separates it out, and the low noise amplifier and the mixer, we get less, and it's still a small signal, and it goes through the low pass filter here to get rid of these signals here, and it goes into the variable gain amplifier. So it takes the gain, and when we add a lot of gain to our signal, because it's a soft signal and we want to make it loud and make it hurt. Alright, and now filters in depth, because you take one low pass filter, add it with a high pass filter in cascade or in series, and that's how you get the band pass filter. And in theory we want an ideal low pass filter, but that's not possible. So we have the transition band, which the sharper the transition band, the cost is more ripples in its passband up here. And from that, to play with the slope, you have to mess with the order of the poles, getting more or less of them. And from there, you can talk about the antenna. And with the antenna, you have the main radiator, which is here, and that emits mostly along these branches and these branches, giving the main radiation plane along the arrows from the dipole antenna itself. And we have the differential strip line, which we've learned about, which is basically a microstrip line, and you can calculate the impedance along it from its length and whatnot. And then you have the printed balloon, which takes unbalanced, it'll add current positive and negative to each side instead of ground, so that way one side is no longer grounded and it will balance your signal. And in the middle of the top and bottom circuits is the dielectric, which allows for the radiation to be emitted in a certain dipole region along these arrows, which is perpendicular to the dipole antenna itself. And from the length of the antenna, we want it to be in similar order to its wavelength, so that the physical length and the electrical length match up. Technically, that's why we wrap it from top and bottom, because it's about 1/2 meter in this diagram specifically. And that's how we intercept the receiving signal, go through the entire circuit again, and grab the soft radio frequency signal and amplify it without noise. And basically that's a rough summary of how this system works. Alright, thank you so much for your time. Hope you learned something by watching. Thanks.